Welcome back, Troopers, to the Solar Power Diverter Part 2. If you haven't watched Part 1, Update 60, please do so. It's got some very good information in there, but also a whole list of off-the-shelf products that you can buy. However, if you want to build your own, definitely watch this video first and then obviously have a look at the links down below. Now with this video, please remember that this is all mains voltage when you're switching AC, and the second part, or the other part of the circuit, is all mains voltage. So while testing and playing around with this and building a unit like this, just be very, very careful. If you're unsure about mains voltage, just buy the off-the-shelf product. It's the easiest way to go. You can just get an electrician to install it. However, the DIY version of this can be built for less than $100. My cost of it was about $150. The biggest cost for me was actually the enclosure or the box to put everything in. But apart from that, if you've got an easy source for things like the ABC boxes and anything like that, or the heat sinks and anything, then obviously you'll save money on this build. And the rest of the parts are actually really cheap. So with that being said, let's jump into it. So first of all, what's the difference between the off-the-shelf product and the DIY version? First of all, there's a couple of things. The off-the-shelf version, you don't have any control over. It's closed-sourced versus open-sourced. That's really your difference. You can't, with the off-the-shelf product, it's going to be a little bit more harder to integrate with your monitoring system. It's pretty much going to be its own product on the wall, and it does its own thing. Versus the DIY version, where you can integrate it with whatever monitoring system you've got for your solar or for your power use in the house. It's obviously fully customized. The code's all open source, so you can play with it, add code, do what you like. There's a bit of a community around building this type of product, and that's really your key things. One is obviously closed, and one is you can play with it what you like. I went down the DIY path mainly for that reason. I wanted something that would integrate with my solar monitoring, and that way I can kind of keep an eye on it, and I can make changes later down the track if I ever wanted to. So how is the power varied? Well, it's far too complicated for me to explain in this video. What I'll do is I'll link it in the description below where you can read about the builds. There's a DIY section where you can kind of go through. It clearly displays how it works, how the power is varied, how it's using the triac or the SSR to vary the power sent to the hot water cylinder or to the load. So I'll link that information in the description below, mainly because it's too complicated to explain. But there's a couple of different ways and various systems to use. So have a look at the links down below after watching this video, and that'll kind of help you understand exactly how the power is varied towards the load or the switching of the high voltage to the hot water cylinder. So a quick recap, how does it work? It pretty much monitors how much power is being exported, and it turns up and down the hot water cylinder based upon that. So it's constantly looking at how much you're exporting, and it's constantly varying how much power is going in and out of into the hot water cylinder. So for example, if you're exporting 100 watts, it's going to turn the hot water cylinder up so that it also matches 100 watts of load. If you start exporting, for example, 500 watts, it's going to turn up the hot water cylinder to match the 500 watt load. So for example, the hot water cylinder will be running at 500 watts and you won't be exporting anything, it'll be zero. And it'll get to the point that you'll be sending, say for example, 2 kilowatts to the hot water cylinder, and you might have a little bit more solar, so it'll start exporting. But pretty much what it does is it's constantly monitoring how much power is being exported. It tries to match that with the load of the hot water cylinder or the element or whatever else you've got connected to the power diverter. So that's kind of how it works very briefly. So my build of the power diverter is based around Robin's build. What he's done is he's got a website, a UK website. He creates kit sets that he can send out to you if you want to just buy a kit set, which is obviously a good option. But he's also got a ton of information. He's written all the code so you can just download it or copy it. He's got there's lots of information and lots of comments in the old Open Energy Monitoring forum, as well as some of the stuff in the new one. There's tons of information, and he's kind of created a whole website based around making this power diverter. What a lot of us have done is we looked at what he's done. You've even bought a kit set, got him to assemble the kit, send it to you, or you've looked at what he's kind of done, used the code, and also built your own one based around his plans. And that's exactly what I did with my one. Right, so what we'll do is we'll first start off with looking at some builds of other people's, and then we'll jump into what I did with my build and the different variations of what I did after looking at what other people have done. So first of all, let's kick things off with looking at what other people have done. So looking at this first build, we've got the CT clamp that's used to determine how much power and the direction of the power. That goes to a full custom board that someone's created. You've got the heatsink on the right hand side that's connected to the triac, the chip. You've got the custom board that someone's designed has got the 2 transformers on it. So that's doing 240 volts or 110 volts down to 5 volts. That 5 volts then goes to the Arduino Uno that runs all the code. That's a nice tidy little build, but it only contains one CT clamp. Now if we have a look at this next one, what you'll see, this is actually Robin's design. So you've got on the left hand side, you've got the transformer, you've got a full custom board that he designed, you've got the switch is actually at the top of this photo, you've got the triac on the right hand side that connects to the heatsink. As you can see, it's soldered to a PCB. I actually don't like that design, and I've changed it in my design, but it goes to a PCB board that contains the opto-isolator, which is what's used to turn using the 5 volts, which is used to turn on and off the 240 volt triac, for example, or the high voltage side, and that's kind of how this one works. Next one is, this is actually quite a nice clean design. It's based upon exactly the same thing. It's based upon Robin's design as well. On the left hand side, you've got a custom board that someone built that uses the transformer on board. That also has got the input circuit on the same board. So at the very top of that, you've got the RJ or the headphone jack kind of plug that's used for the CT clamp. That all connects to the Uno, which then does all the compute. That turns on and off the opto-isolator, which is on the other PCB on the right hand side, which has got the triac soldered directly to it. And at the top you'll see you've got the input from the mains power, you've got the output of the mains power. You'll see, looking at this, you've got the earth just looping back to the earth, so earth's to earth. You've got neutral to neutral, and you've got the live that actually is the only one that actually goes down and connects to the triac. All the rest are pretty much looped directly to each other. That's what I used in my design. It's nice and simple and quick, and it's nice and tidy. So having a look at that design on the wall, that's kind of how it looks. It actually looks pretty good, and this is the kind of design that I based mine on. Obviously the same photo again with the lid on. No display, it doesn't really need a display, but that person hasn't done a display. The bottom, this next one here is actually a 3-phase version of it, so that you can have 3 different triacs that's running 3 different hot water cylinders for each of the phases. And it looks a bit messy, but that's because there's just so many wires that need to fit into a small box. So with my one, what I wanted to do was not put the transformer on the board, and I wanted to keep that part as simple as possible. So all my AC stuff, all my high voltage main stuff is simplified. That way there's less risk. So with my one, what I've done is I've used normal power adapters that you might have lying around. I used a 9 volt one and a 5 volt one. A normal 5 volt one that you plug into a wall for power for charging something or whatever. I use those ones rather than connecting a transformer and customizing a PCB. That way there was less risk, or at least that's the way I felt. It does mean it's a bit annoying because obviously you've got more plugs that you need to plug in to make this device work, rather than just having a box on the wall with kind of everything inside. I've got a couple of things that are separated, but it does mean that when building this, everything's simplified on the AC side. It's only the only thing that's connected to the AC is the triac. Everything else is external and using off-the-shelf things. So that kind of made it a bit safer. Remembering that this was my first build a year ago, I'd never connected anything like a Arduino and coded and never done anything like that. So this was kind of jumping in the deep end. So in saying that, let's jump into some photos. As you'll see in this first photo, we've got the triac. This is what the triac looks like. It's connected directly using the 3 cables. The main reason I did the 3 cables and I didn't connect it to the circuit board like other people have done is that the circuit board's the first part of failure. What happens is that the PCB with the triac connected to it, there's a lot of current going through that PCB, and that becomes a point of failure because of bad soldering, cold soldering, and I've seen photos of that part being burnt out. If anything, that's the part that's going to fail, is going to be the high current side. So when switching 3 kilowatts or 2 kilowatts for your hot water cylinder, that's a lot of current that you're switching or varying. So that means that that's PCB, or that circuit, is the part that's going to get heated up if the tracks aren't big enough, and it's just risk. So I alleviated that completely, and what I did was I directly connected my AC cables to the chip itself, and then that goes back to the power block. So next pic, you'll see that the triac is at the bottom there. It goes up to the power block, and then that goes to the PCB. The PCB has the opto-isolator, for example, and that's what switches the triac on and off. So we've got nice thin cables going to the power block, and then the power block to the triac is much thicker cables, but that's the only mains voltage components of the circuit. So if we have a look at the next photo, this is the input side. So this is where the CT clamps connect to. You'll see we've got some resistors, we've got a whole bunch of stuff on there, and that's where the CT clamps connect to. This next photo, you'll see that these is the 3 kind of parts separated out. So we've got the input side, we've got the Arduino for the computing side, and then we've got the output side, which is the triac and the power block. So as you can see on that power block, I've got the live coming in, all the rest is directly connected together, and then the only thing that's not is it goes off to the triac. So pretty much the live and the load is pretty much directly connected together, apart from the live cable, which is obviously the one that's switched. But that means it's nice and simple because there's only pretty much one cable that comes off that. Again, this is a closer look at it. So this is what I did while testing. The connection block there, we've got the live cable comes in. You'll see that I've got the 2 CT clamps there that I was using for testing. I've put the heatsink on for this time, and we've got the triac obviously on the left there, and that goes up to the circuit board that under the tape. The reason I put the tape on there is because obviously we've got a couple of thin live cables going to there, which is doing the switching of the triac. So there's 240 volts going up to that circuit block, up to that PCB, in which case I wanted to put a piece of tape over it so there's no risk of me accidentally touching it. Coming through to the next photo, what we've got is me testing things. I had some LEDs kind of there. You'll see the box that I've used. You see the part that I was going to cut out that's where the triac will sit under. So I cut that part out, and you'll see me doing some testing. Next part of this, you'll see now I've got the triac in the box with the heatsink mounted. We've got the bottom PCB there. I hot glued those cables so there's no way that those cables are going to move, and everything else is nicely tight in there so that even if there's pretty much there's no risk of movement and things coming loose. But also you'll see that the ground cable connects directly to the heatsink, and and obviously there's tons of room on the heatsink for more triacs if we want to control more loads. So next pick is obviously the heatsink with the box with the lid on top, so that's kind of the whole unit coming together. So now all the 240 volt stuff that you see on the last photo is now in the box, which means that now it's much easier and safer for testing. And I've got the other parts that are external that now I'm testing with some extended wires there. So I'm using that to kind of figure out the code and understand how the code works before moving on to the next part, which is kind of putting it all together. This next photo is obviously as things are slowly coming together. It's just another angle of things. Go to the next photo. Again, another photo of the testing as well. You see that the CT clamp is at the top. Another CT clamp is this time inside. The reason for the two CT clamps is that the clamp inside is the one that's monitoring how much power is actually being delivered to the hot water cylinder, so that we can keep an eye on it, knowing that how much power on each day is going to the hot water cylinder for monitoring. So that's why that's going to there. So next part was, well, now that I've got it all into a box, I actually need to connect the CT clamp up rather than into a testing circuit, rather than testing it with a light and other bits and pieces. Now I actually put the CT clamp around the mains cable that came into the house. while it was a sunny day. That way you'll see on the bottom there, I've got my laptop set up, I've got a light and I've got a heater. Next photo you'll see again, you'll see the laptop, you'll see the box, you'll see the CT cable that goes up to the wall. You'll see that I've got a couple of power boxes, a couple of adapters down the bottom. Again, the light and the heater. The heater and the light is what I'm using for the load to simulate the hot water cylinder. So that kind of shows that the circuit's kind of coming together. Next photo, what we've got is everything kind of in the box. And what I've done is I've labelled the inputs on the outside of the box. So I've got the DC, the 5 volts DC. I've got the AC 9 volts. And I've got the CT clamp that connects to the main switchboard. The other CT clamp again is inside there. This time I've got a big loop of cables because I was using it for testing. Again, you can see the triac in the top corner. You'll see the circuit board on the right hand side, and while that looks a bit messy, it's not. The next photo again is pretty much a different view of the same one, so pause the video if you need to. However, on this one what I've also done is you'll see that I've got the RF chip that's directly connected on top of the Uno, and that way that's what I'm using to send all the information off to my monitoring system. So now that I've gone this far, now I've got the shield that sits on top, and I've used that to solder the RF module to the top, which is an RF69. Next part, what we've got is I've shortened the CT clamp cable that sits in the box. Obviously it doesn't need to be really long. I've got my USB cable plugged in for some testing. That's pretty much what things look like. I've got the 2 power adapters coming in from the other side. I've got the LED light on the top and the middle part, which is a green light, and I've got a red light which shows my 5 volts plugged in. Next photo, if we have a look at that, again you'll see that the LED is lit this time. So that means when it's completely lit, a full amount of power is being sent to the hot water cylinder, and that's kind of how that's looking. If we have a look at the next photo, again it's the same thing, just on another angle, so you can pause that if you need to look at it. Next one is what it looks like on the wall. So this is actually how it looks like on the wall a year later. This is me taking a photo just a couple of days while trying to get this video out. So you'll see that that's how it looks on the wall with the cover off. Well, I haven't shortened any of the power adapter cables for the 5 volts and 9 volts. Obviously I could do that to tidy things up, but that's kind of how that looks. The next photo really is, this is how it looks like on the wall just the other day. I've got those 2 cables going in. That black cable is the CT clamp cable that goes down to the power board that's just next to it. In this photo here we've got 5 volts plugged in, and we've got the mains, we've got the hot water cylinder receiving power from this unit, the green light's on. And last photo, this is how it looks normally 99% of the time. Now a lot of the first questions is that, Michael, there's no display. Well, you only actually need a green LED on there to tell you that there's power being delivered to the hot water cylinder, and you can just glance at that to see if there's power, and it turns on and off. So what I'll do is I'll quickly show you a photo, a very quick video I took the other day, and it will show how the LEDs lights up. But pretty much there's no big display on the front. The reason I didn't need a big display is I don't spend my time in the laundry, and I've got all that information using that RF chip being sent to my monitoring system, and that's what I use to monitor what this is doing. So I actually don't need a display. The other thing is that by not having the display on here, that meant that I can simplify. I needed less stuff on the circuits to be able to not drive a display. That made it more simple to build, and remember, this is my first build in something like this. So let's have a look at that video. So if you have a look at the green LED in the bottom left hand corner of the screen, you'll see the amount of times it flickers. So that's how much power is being sent to the hot water cylinder. So that's our indicator light. That's directly connected to the triac pretty much, and it just shows you what's being sent. So if that's flickering fast, more power is being sent. If it's flickering less, then a little bit of power is being sent. And right now, as you see, it's now sending more power to the hot water cylinder. So the sun's in a much better position right now. It's a very cloudy day, but so it's kind of a bit hit and miss. But as you'll see there, it's now sending a good amount of power, and the speed of which that light flashes continuously changes, as you'll see, mainly because it is directly connected, so you definitely see exactly what's happening with the hot water cylinder, which is quite nice. So that kind of gives you a good understanding about what I did with my build. The video's been a bit longer than I thought, but it does help with if you are building something, then obviously take into consideration kind of what I've done and to simplify it. However, some of the things that I would improve on the next time if I was to do a version 2 of this would be I would put the transformers inside the box. That just means that there's less kind of plugs and power adapters and bits and pieces needed to make it functional, so I possibly would do that, and that way technically you wouldn't need to put it by the fuse board, you could put it by the hot water cylinder, you can move it around because it's wireless, it's sending the data off. So I would put the transformers in there. Now that I understand a whole lot more about AC and how this works, I could obviously do that in version 2. The other key part of version 2 would be looking at the code and adding some extra things in there. Like I mentioned in the first video of this update 60, what I would like to do is that if the unit decides that there's not enough power being sent to the hot water cylinder by 6 o'clock at night, for example, because it's been a cloudy day, then rather than turning the hot water cylinder on, first of all I would like it to look at the weather. If it's wet and rainy tomorrow, turn the hot water cylinder on. If it's not wet and rainy the next day, for example, if the weather forecast is sunny, then don't turn the hot water cylinder on. And the reason I say that, and that would be an enhancement, is you can always have an override switch, but that would mean that there's normally enough hot water in the hot water cylinder, even if you don't send a lot of power to it because it's been a rainy day. There's normally enough hot water in there to get you through a couple more showers that night, which is normally enough. And if it means that you can get through that night without spending money on power to heat the hot water cylinder, what it means is that the next day, if it's nice and sunny, you're going to put that power back into the hot water cylinder and heat that water. So it's not a problem. It's only a problem if that next day is raining. If the next day is raining, then obviously we need to heat the hot water. You might as well heat it now than heat it in the next day because it's still raining. So there's just some enhancements that we could do there, and you can always have an override switch, but just by knowing what the weather's going to be like. And the reason I say all that is because I've looked at the graphs and the data over the last year, and there has been a couple of days where the hot water cylinder or the power diverter has turned on to send power to the hot water cylinder when we didn't have to, because actually no one had a shower that night, and we spent $2 worth of power that night when the next day was sunny, and it was so sunny we could have filled up the hot water cylinder with hot water. So that's why I would have put that enhancement in there, and that maybe I'll look at that going forwards later down the track. So realistically, where to find all the parts, look in the description below. Have a look at the Open Energy Monitor forums. There's a whole lot of information there. However, most of it's in the old forums. That's missing some photos and bits and pieces, so it is a little bit harder to find. However, talk to Robin. He's put a whole lot of effort into creating the code and to do it. He's got all the download links on his page. If you want to buy a kit, obviously just go to him. If you live in the UK, then have a chat to him. He's obviously local towards you. However, me living in New Zealand, it was easier for me to just kind of build my own with parts around. Now, as I said, the cost of this for me was about $150. The main reason is that I spent $47 or $48 on the actual ABC box itself. That was the most expensive component. Everything else is cheap, so you could build it for less than $100. However, if you think this is too complicated, if you don't understand enough about mains voltage, then obviously buy the off-the-shelf unit. However, it's good to tinker around with. It's a massive learning curve for anyone that's kind of learning about this type of thing, and it's a good project to kind of get underway. So again, thanks again for watching, guys. Hope you enjoyed the video. Thumbs up if you like it, and I'll see you in the next video. Thanks, guys.